or topic 1.4, and this is about polynomials. So a lot of this is probably stuff you've seen before, but we want to emphasize it, and then there will be some new stuff too. So first, a polynomial is anything in this form. So p of x equals an x to the n, an minus 1, x to the n minus 1, and so on, where n is a positive integer. Okay, so n, the powers, cannot be fractions, they cannot be negatives, but they're positive integers. And ai is any real number. So these an are just real values. The coefficients can be negative. The coefficients can be fractions. That's fine. The leading term is this first term here. Okay, and then we kind of break it down further. The highest power is going to be the degree, and if it's written in standard form, meaning highest degree to lowest degree, it'd be the first one. It doesn't always have to be the first one. But the highest degree is your power, and then the coefficient for the term that has the highest power is our leading coefficient. So, in this first one, okay, my degree is going to be 4, because that's my highest power. My leading coefficient is the coefficient of that term. So we get a 3 there. The next one is not written in order, okay? And you could write it in order if you wanted to, if that makes more sense for you. But I think at this point you can tell that's our term that we care about. My highest power is 3, so my degree is 3, and the coefficient there is -7. The last one, the degree would actually be 0, because if we had a power of x and there's no x, that means the degree would be 0, and the leading coefficient would just be 4. Extrema. Okay, extrema are going to be the maximums and minimums of the graph. And there's kind of 2 categories for this. There is relative extrema or local extrema. So local and relative are the same thing. So if you see that term, they're interchangeable. Then there's also absolute or global extrema. Okay, relative is anything that is a maximum or a minimum for its little part of the world. Okay, so pretty clearly we've got some maximums here and here. I've got a minimum here. So I have, and then this graph is kind of funny. You'll notice that there's a closed dot here, and then it goes, and then it has an arrow on this end. Since this has a closed dot, we're indicating that we're ending the function there, which means this will also be a minimum, because for its little part of the world, it's the lowest value. So we have minimums at x equals -4, and at x equals 0. We have local maximums here and here at x equals -2 and x equals 3. Okay, we have the same graph over here, and now we're looking at absolute maximums or global. Okay, so absolute and global are interchangeable. So the absolute max or the absolute min is the absolute biggest output value on the graph or the absolute lowest output value on the graph. Okay, so for my absolute maximum, okay, there is nothing on this graph that is higher than that point there. Okay, the value of that is 2. So we say the absolute maximum is 2, and it occurs at x equals 3. You may be asked for what is the maximum value. You may be asked for where is the absolute maximum value. Or you might be asked for both. Absolute minimum. Okay, so this has an arrow here, which means it's going to continue to plummet down to -infinity. Okay, so there is no absolute minimum on this graph because of this arrow. Had this been a dot, if we had stopped the graph here for whatever reason, then it would, and it would be that value there. But since it has an arrow, there is no absolute minimum on this graph. All right, so we're going to find and classify each type of extrema, or write an A or there's none there. So relative minimum. This graph just continues to go down, so there is no relative minimum. There is, however, a relative maximum. Okay, this point right here is bigger than the values close to it. So that's a max at 1. Again, the arrows go to negative infinity, so that means there is no absolute minimum. Sorry. No, you're good. So then absolute maximum, there is an absolute maximum of 3 at x equals 1. So that one extrema that we have there is both a relative maximum and an absolute maximum. New graph. This one does not have an arrow here. It does have an arrow over here. So relative min, we've got one down there at x equals -2. Relative maximum, because I have a closed dot here, that one counts, and that one counts. So relative at -4 and 3. And absolute. Absolute minimum, there is not one again, because this arrow indicates that it's just going to keep going. Absolute maximum, there is no value in this graph higher than this point right here. So the maximum value is 2 at x equals 3. Okay. This next one has 2 endpoints. So it's going to have both an absolute max and an absolute min. But I want you guys to try that one out. Okay. So we have relative maximum or minimums here and here. So -3 and 3. Relative maximums, I've got this point, and this point. So -4, 3, and 5. And then the absolute minimum value, the winner of that prize is -3. At x equals -3, our y value is -3. And the winner for the maximum is that guy right there, with a value of 4, which occurs at x equals 5. This 3 is not correct. That should be a 0. Sorry about that. So the x values is what we're interested in, not the y values, unless you're asked for it like here. Fun facts about polynomials. All right. Fun fact number 1, between 2 real zeros of a polynomial, there must be at least one local max or a local minimum. And I'll draw a picture to explain here. Okay. So if I had a graph, and if we know we have real zeros mean the output is 0, and if it's real, that means it's on the x-axis. As long as it's not the line y equals 0, which would be a horizontal line here, the only way you can have zeros is if it goes above and below. So here, between any 2 zeros, there must be a local max or a local min. The other fun fact, and this will get tied in when we talk about end behavior in a couple of days, polynomials of even degree, okay, either have a global maximum or a global minimum. Okay, and again, we can use local or relative, we can use global or absolute, they just mean the same thing. Okay, so even degree polynomials, like a parabola or some other higher degree, is always going to look like that or that. And we're going to talk about end behavior in section 1.6, but because the ends either go to both positive infinity or negative infinity, there must be an absolute min or an absolute max. Odd functions do not have that same feature. Odd functions will not have a global max or a global min. Okay. We've been talking about concavity quite a bit. We talked about concavity in 1.1 when we looked at just the graphs and determined concavity. Then we related it to the rates of change, which we're going to do again. But when we have a graph that changes concavity, so this graph here is concave up, concave down, concave up. Where the change happens is what we call a point of inflection. Okay, so on this graph, like I said, we're going concave up, and then there's a point right here at -1 where the rates of change go from increasing to decreasing. Our slopes are going up, and then they start going back down. So it's concave down, and then it starts being concave up right here. Okay, so the graph has 2 points of inflection for this one, at x equals -1 and at x equals 1. We're looking for that change in concavity. The follow-up to this, kind of relating back to what we've been talking about, for each of the following intervals, determine if the rate of change is increasing or decreasing. So I'm just going to make a reminder note here. So we've been talking about this graphically, we've talked about this numerically, but if our graph is concave up, the rate of change is increasing. If the rate of change is increasing, then our graph is concave up. If the graph is concave down, that means our rate of change is decreasing, and vice versa. If we know the rate of change is decreasing, that means our graph is concave down. So we're going to determine that from the graph. So I know the concavity pretty well, we can see that, so then I can determine whether the rate of change is increasing or decreasing based on that. So the interval 3, 4, so we're looking here. The graph is concave up on that part of the graph. So my rate of change, I'm just going to abbreviate there, is increasing. And my justification is that it is concave up. Okay, for -4 to -3. So now we're over here. It's the graph itself is decreasing. But it's concave up again, which means the rate of change is still increasing. And my justification from the graph is concave up. And sometimes, just depending on the question, we might say it's concave up, so it is the rate of change increasing, or vice versa. -1 to 1. We're concave down there, so my rates of change will be decreasing. Okay. And I don't know why I said increasing, is increasing, because the graph is concave down here. Okay, and then our last one, 1 to 2, we're back to concave up, which means my rates of change are increasing. Because of our concavity. So we talked about what makes a polynomial. I want to show you some non-examples, things that might kind of look like a polynomial but aren't. So the first example is something with a negative exponent. If the exponent is negative, it is not a polynomial. If we have an exponent that is not a whole number, okay, that is not a polynomial. And the last one I'm going to draw is if the base is not x, it's a number, and the variable is not a number, it's an x. This is actually exponential and not polynomial. So all of these are not polynomials. So our last example is for 0 is less than or equal to t is less than or equal to 3. The number of cars in a parking lot at time t hours can be modeled by the function, that big polynomial there. Based on this model, at what time t does the number of cars in the parking lot change from increasing to decreasing? So we are going to use our trusty calculator. Okay, so the first thing I'm going to do is type the equation in, replacing the t's with x. So we need to find our window. So from from 0 to 3 is going to be my x min and max. So I'll go to window and do 0 and 3 because my starting input value is 0, my ending input is 3. I don't care what happens after 3. I don't care what happens before 0. For the y values, we want to know the number of cars, okay? And you can guess, but we have a tool that'll help us. Okay, we're going to be using the table to see what happens to the value. So above the graph is table, but before we do that, we want to go to the table set. So above window, it's table set. So we do second table. And yours might be set to a default or not, but we want to start the table at 0 because I want to see that. And you can go by whatever delta, but I'm just going to go up by 1s. And you want to make sure these are both auto. Okay, so again, you go to second table set and set that up. Now we actually want to look at the table. So if I do second graph, we have that table button. And now I can see what numerical outputs I'm getting. Okay, so at 0, it's at 3, 1's at 5.5, 2's at 25, 3's at 8, and then it becomes negative. Okay, which is why we're only looking from 0 to 3 anyway. Okay, so we need to pick a value for my y's. I don't care about negative cars, so we're going to start our y's at 0. And before I go back to the window, the biggest value I know I'm going to see is a little bit bigger than 25. So we want to pick a window that's bigger than 25. Okay, so let's go to window. I'm going to start my window at 0. And what might we pick for our y max if we want to see at least 25? Okay, pick a number bigger. 40 is bigger. It's not too much bigger. It's probably not realistic to go up to like 100 or something. And if you pick a number that's too little, like you do like 26 for some reason, you might need to adjust, and that's okay. Then we graph. Okay, we've got our window, we've got our graph, and we want to find where the graph switches from increasing to decreasing, which is this value right here. To find this location, we're going to go to another one of our blue guys up here, to the calc menu. So do second calc, and there's lots of different things in here that we're going to be using throughout the year. Value is just the value. You can locate a 0 using this menu, a minimum, a maximum, intersection we'll use pretty frequently. For this scenario, which one do we want to use? Okay, so we're going to go to maximum. And then it's going to ask us 3 questions. It wants us to bound the maximum. So it's going to ask for a left bound. So we want a number lower than our maximum. We're going to go up the hill here. Pick a value somewhere on the other side of that maximum. And then it wants us to guess. Okay, so that was section 1.4 on polynomials and rates of change.